Okay, section 1.6 is on logarithmic functions. So I'm hoping, again, this will be largely a review for you. I know logarithms aren't the easiest concept to get, especially the first time you're learning it or even the second time you're learning it. So I'm hoping this will be a good review, but also help deepen your understanding of what logarithms are. So logarithms with a base b, any logarithm with base b is the inverse of an exponential function with base b. So logarithms are inverses of exponential functions. So an inverse meaning they cancel each other out or undo each other, just like addition is the inverse of subtraction, or subtraction is the inverse of addition. So those two things cancel each other out or undo each other. So this is why logarithms are so important to us, is because they allow us to solve exponential functions when the variable we are solving for is in the exponent. So here's the formal definition of a logarithm, and this is a definition that you might want to commit to memory. It will be super helpful if you do. So let b be not equal to 1 and a positive real number. Then for all positive real numbers x, y equals log base b of x if and only if, that's what the double arrow means. So if this is true, then let me make that better. Then we can also rewrite that whole thing as an exponent, because again, logs are just inverses of exponents. So we can write that then as x equals the base b raised to the y. So that's the formal definition, and I'm hoping this looks familiar to you, and it's super helpful if you just have this all memorized. So I want you to pay attention to where these letters are in each of these two equations. So, and then that hopefully will help you remember it. So log, the base of the log, if you rewrite it as an exponent, is the base of the exponent. Whatever you were taking the log of, so in this case we were taking the log of x, that is what the exponential expression equals if you write it as an exponent. And then what the logarithm equaled, let me get a different color. What the logarithm equaled, which originally is y, is the exponent of your base. So if you look closely, you can see that a logarithm is really just an exponent. And what I mean by that is you've got y equals this whole logarithmic expression. But when we rewrite that as an exponent, y is the exponent. So logs are really just exponents. Okay, so a logarithm with base 10 is called a common log. I'm hoping you've heard that before. And you can write common logs as log base 10 of x. That would be a common log of x. Or if it's a common log, we just can actually leave that base 10 out. So if there's no base specified, you will assume that it's a common log or base 10. A log with a base of e, remember e from the last section, is called a natural log. So that would look like log base e of x, which you're probably not used to seeing it like that. You're probably used to seeing it as an ln of x. So ln of x is the natural log of x. Okay, we're going to look at how we can use this definition of a log to rewrite some logarithmic expressions. So we can use the definition of a log to write, and I'm really just going to rewrite what we wrote above. Y equals log base b of x. Now, if that's true, then I'm going to rewrite that as an exponent. That would mean that x equals the base of the log b raised to the y. Now, if that's true, I'm just going to do some substitution here. Like I just mentioned above, y is equal to this whole thing. So I'm just going to substitute that in. So x equals b raised to the, now instead of y, I'm writing that whole thing, log base b of x. Now this seems silly to write x like that, but it's helpful because if you see what's happening, you've got an exponent here to the base b, but if the exponent itself is a log with the same base as the base of our exponent, so here's our base of the exponent, here's the base of a log. If those two things are the same, then it simplifies to that, which is right here. So if you have a base raised to a log with the same base, then it simplifies to simply whatever you're taking the log of, which is x. So we can see in example 1, 3 raised to log base 3 of 7. Those are inverses of each other. They're going to cancel each other out, so that just equals 7. 10 raised to the log of a. So there's no base specified on that log, so we assume it's log base 10, which means we've got the same base of our exponent and log, so those are going to undo each other, and you've just got a. In part C, you've got e raised to the natural log of 21, so we've got base of e raised to the natural log with a base of e of 21, so that just simplifies to 21. So that same idea applies if you kind of look at it in the opposite order. So instead of a base of an exponent raised to a log, now you've got a log of something, another base raised to an exponent. And the same thing is going to apply. So I've got log base 4 of the base 4 raised to the 9th power. So this is all going to undo itself, and it really just equals 9. So anytime your base of the log is the same as the base of the exponent in the log, those cancel each other out. So log of 10 raised to the a. Remember, that's log base 10 of 10 to the a. Well, if same base there, it's going to cancel out. So you just have a. And then natural log of e raised to the pi. Again, this is log base e of e raised to the pi, so that's just going to be pi. This next set of examples is using the definition of log to evaluate these. So evaluating is what is the actual answer, what's the numeric value for that expression. And looking at it at first glance, you might think I have no idea, but let's use what we know about the definition of logarithms. So I'm going to come right back up here. If we right here we've got log base 10 of 1,000. So we can link that back up with what we know and then rewrite it as an exponent. So usually this equals something. Y equals log base b of x. Right now I don't have that y equals, but you can just go ahead and write x there, and then you've got everything you need to solve. So the base of the log is always the base of your exponent. So my base of my exponent is going to be 10. The base, or this answer here, is going to be the exponent of 10. And it's always going to equal whatever was inside of the log. So just like this, whatever was inside of the log here equals the exponential expression there, which is 1,000. So we've rewritten this logarithmic equation as an exponential equation. So 10 to what power equals 1,000? So I'm hoping you all know that 10 cubed is 1,000. So 10 squared is 100, 10 cubed is 1,000. So that would mean x would have to equal 3. So let's do the same for this next one. Log base 1,000 of 10. So it's just reversing where our 10 and our 1,000 are. So I'm going to put an x there, and then I have everything I need to rewrite that as an exponential equation. So my base of the log is going to be the base of my exponent, 1,000. Sorry if you can hear my kids partying on the monitor. They are supposed to be napping right now. Okay, so 1,000 raised to the x equals whatever you were taking the log of, 10. So this one looks a little trickier right off the bat. 10 or 1,000 raised to the x equals 10. Well, how is it that when you're raising 1,000 to a power, it's getting smaller? That would mean that x would have to be a fraction, and it's going to be the opposite of this problem. So that would mean the cubed root of 1,000 equals 10. So that would mean x would have to be 1/3. And then lastly, put an x over here on C, and then rewrite this as an exponential equation. So base of 7, so 7 raised to the x equals 49. And 7 squared equals 49, so x has to equal 2. Okay, turn the page. More examples like this. So I encourage you to pause, go through each of these on your own, get the answers, and then check it, and we'll move on. Okay, so you see the answers here, and after working through these, I decided I should probably talk about them. So the first one, log base b of 1 equals x. So when I rewrite that as the exponential form, that would be the base b raised to x equals 1. So it doesn't matter what b is, because anything raised to a certain power will always give us 1, and that's when you raise anything to the power of 0, you get 1. So regardless of what b is, the only way you could get 1 by raising it to a power is if that power is 0. On e, I rewrite that as the exponential equation. So 81 is my base, raised to the x equals 3. So 81 to what power equals 3? And again, that seems confusing because how can I raise 81 to a power, meaning multiply 81 by itself and get a small number like 3? That means we're going in the opposite direction of what we're used to. But if you think of it in the inverse direction, so 3 raised to what power is 81? That would be 3 to the 4th. So if 3 to the 4th is 81, then 81 to the 1/4 equals 3. And then lastly, this just follows right from how we used the definition on the last page. Log base a of base a raised to the 4th. Remember, that's going to undo each other, and you're just left with 4. Okay, next we're going to do kind of what we did in the last section where we were analyzing different functions, where we looked at all of those different things like domain, range, increasing, decreasing, maxes and mins, those 10 things that we used from earlier in our notes. So we're going to do that with a logarithmic function. So the first thing you want to do is graph this function on your calculator and sketch the graph over here. Make sure that you are aware of any asymptotes here because we will be looking closely at that and a new way of looking at end behavior. So we're going to introduce a somewhat new concept on this one. All right, I wanted to show you the graph of this on my screen in case you're seeing the same thing on yours. So you can see when you graph this, it looks like it just stops right here where x is about negative or x is about 4. If I trace it, and so right now there's my tracer, and I'm going down, x is getting smaller. So as you see, as x gets smaller, somewhere in between 4 and 3.9, my y isn't defined anymore. That doesn't mean that the function just stops. Our calculators are limited to the images that they put out sometimes. But if you look at your table of values here, where were we? We were at 5. Whoops, at 5 I'm at 0. Let's see, at 4.5, I'm there. At 4.1, I'm there. At 3, error, because it's undefined like we saw on the graph. Well, let's see if I can get closer and closer to 4 though. So if I do 4.001, I'm at -6. So I'm getting pretty close to 4 from that left-hand side, and I'm still defined. How about 0.0001, -10? The calculator, you'll see, is just rounding that to 4, even though I typed in 0.0001. Now I'm going to do even more zeros. -12. I'm getting very, very close to 4. Oh, that one's just rounding. But you'll see that the calculator is getting lower and lower on the table. So while the graph isn't showing it, this line does get very, very, very close to the x value of 4, but never reaches it. Okay, so now that we know that it will help us graph this, we can conclude from that last video on the calculator that there is a vertical asymptote right here where x equals 4. Which I'm hoping might make sense to some of you, because think about what would happen if I plugged in 4 to my equation. That would mean I'd be taking 2 log of 0. You cannot take the log of 0. It's not defined. So this would be a domain restriction. X has to be greater than 4. We can't take the log of 0, and we can't take the log of negative numbers. So hopefully it makes sense that we're only looking at this part of the graph. And no smaller than when x equals 4. And then our graph looked like this across there. And it got very close to 4, but never touches it. Okay, so now we can go through a process of analyzing it. So the domain of this I just talked about. Remember, we can't take the log of a negative number, which means that we can't plug in anything less than 4 or 4, which means our domain would be 4 to infinity. The range, so we're looking at output of the function. Over on as x gets closer to infinity, larger values of x, this function is going to continue to grow. So I know that my y values are going to continue to get higher and higher as x gets larger, but also as x gets closer to 4, my function is just going to keep shooting down, 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 further and further. So really our range spans the whole set of real numbers. So we're looking at a range of -infinity to infinity. Is this function increasing or decreasing? Well, it's obviously increasing. Remember, reading it left to right, it's shooting up very quickly. It will even out a little bit, but we're looking at a strictly increasing function. Are there any maxes or mins, aka extrema? So because it's always getting smaller here, there's never going to be that smallest point. And it's always getting larger as x gets larger, so there's never going to be that largest point either. So there are no extrema. Next, we can look at end behavior. So let's look at end behavior for when x gets larger and larger. And this is where we're going to introduce a slightly new concept with end behavior in limit notation. So our function's name is f of x, and as x approaches infinity, gets larger and larger, so will our function. The y value will also get larger and larger. Typically at this point, what we do next is look at the left end of the graph as x approaches -infinity. So we always, after this, do f of x as x approaches -infinity. But x doesn't approach -infinity here because we already wrote in our domain here, we don't go any smaller than 4. So x doesn't approach -infinity. The farthest thing x can approach, we see with our asymptote, is 4. So x is approaching 4. So we can discuss end behavior by talking about x actually approaching a specific value, but not only what value it's approaching, but from which side it's approaching it. So you've got two sides of 4. You've got this side and you've got this side. Our function only exists from the right of 4. meaning from everything greater than 4. So to note that with limit notation, we put a little plus sign after the 4. So this signifies x is approaching 4 from the right. So that's what that little plus sign means, from the right. If our function was over here, we would say as f of x approaches 4 from the left, and we would just put a little minus sign there. So that's a new concept, but it's pretty straightforward. Some of our n's don't approach infinity or negative infinity, they just approach a specific value. All right, and with that n behavior, we should write our asymptote at, so we're used to horizontal asymptotes, but this n behavior is limited by a vertical asymptote. And this asymptote is where x equals 4. And we've got one intercept, we've got an x-intercept at 5. And that's pretty much it. This also can model population growth. It's the inverse of an exponential function, so a lot of the things that exponential functions can model, it goes the same for logarithmic functions. Okay, now that we've reviewed logarithms, we're going to review properties of logarithms, which are very similar to the properties of exponents we talked about in the last section. So properties of logarithms, I know that you have seen them and worked with them before, but I also know that it doesn't always stick that first time. So hopefully this will jog your memory and just solidify your understanding of these a little bit more. So the first one is when you've got the log of two things multiplied by each other. You can, what I call this, expanding the log into two different logs. And you can expand that by adding two different logs together. So this can be rewritten as log base b of u plus log base b of v. So, and this relates directly to our exponential properties as well. So this is going to be, I'm going to show you why this makes sense to me. So if you've got the log of two things multiplied by each other, you can separate them by adding them. And this relates to our properties of exponents because we saw that if we had a base raised to some power times a base raised to a different power, we could rewrite that as the base raised to the sum of those. So this multiplication became addition in the exponent. And same thing here. This multiplication here became addition between the two logs. So they all kind of relate back to our properties of logarithms. Next we've got a log of a fraction, and just like when you've got exponents with fractions, you subtract, same with logs. So this we can separate into two different logs, and it would be log base b of u minus log base b of v. So this division we can separate into two logs by subtraction. And lastly, and this one is super helpful to us, if you've got log base b of something raised to a power, this power can come down in front and multiply by the log. So if you've got a log of something with an exponent, that exponent we end up just multiplying by the log. T times log base b of u. So if you can ever do that, it makes solving for logarithms much easier. So those are the three main properties of logs that I'm hoping you are starting to remember. So now we're going to apply these properties into this next example. And we're told right off the bat in this example the values of these different logs. So we're told that if the log base b of 5 is 0.7, so we don't know what the base is, but we're told right off the bat that the log base b of 5 is 0.7 and log base b of 4 is 0.6. So it's telling us use that to evaluate all of these other expressions. So log base b of 20. I have no clue what b is, so how am I supposed to figure this out? But if I can rewrite 20 using 4 and 5, well, since I know the logs of 4 and 5, then if I can rewrite 20 with those, then I can use properties to figure this out. So really, this is log base b of 4 times 5. But we just saw above that when I've got the log of two things multiplied by each other, I can split that up into those two things, two separate logs added together. So really, this is the same as log base b of 4 plus log base b of 5. Well, we were told log base b of 4 is 0.6, and log base b of 5 is 0.7. So log base b of 20 is 1.3. All right, so on the next one, log base b of 16. Well, the only way I can get 16 from 4s and 5s is if I just take 4 and multiply it by itself 4 times, or multiply by itself twice. So I could do 4 times 4, or I can look at it as log base b of 4 squared. And then I can use this property here. Remember, if you've got log of something raised to a power, that power comes down and multiplies by the log. So 2 times log base b of 4. But we know that log base b of 4 is 0.6, so 2 times 0.6. So our answer is 1.2. The next one, actually what I think would be a good idea is for you to try some of these on your own. I'll go ahead and explain the rest of them, but now that we've seen a couple, it'd be good to start using your brain and try and get through a couple of these on your own. But like I said, I will go ahead and keep explaining. Okay, so the next one, we've got the log of a fraction. So I can separate that using this property by subtracting two different logarithms. So that's the same as log base b of 16 minus log base b of 5. Well, if you're clever and you realized we already did log base b of 16 right here, then log base b of 16, I can just write 1.2. Or you can go through that whole process again where 16 is the same as 4 squared, and you solve it. But we already did the work for that, so why do it again? And then we know log base b of 5 is 0.7. So that leaves us with 0.5. The next one, simple enough. We've got log, I'm going to switch colors here. Log base b of a fraction again. So I can separate that into two separate logs using subtraction. So log base b of 5 minus log base b of 4, which would be 0.7 minus 0.6. Okay, the last one I'm going to talk through is E, and then I'm just going to pause, finish F, G, and H, and let you do the same, and then you can check your work with mine. So this one I want to explain because we've got log base b of 2. How can I get 2 using 5s and 4s? Well, 2 is half of 4, but we don't have something for cutting a log in half. But what we could do is think of 2 as the square root of 4. So we can operate with 4 in a way to get 2 if we take the square root of it. So think of it like that. But we don't have a property for square roots of a log, but we do know that we can rewrite a square root with a power of 1/2. So really we're looking at log base b of 4 to the 1/2 power. So anytime you can do this, take that power down and multiply it. So really we've got 1/2 log base b of 4. And base b of 4 is 0.6. So half of 0.6 is 0.3. All right, so go ahead and finish F, G, and H on your own, and then you can check your work with mine. Okay, so over on the next page, caution that I want to talk about, and that is when you're using the property where you can split a log of dividing something into two different things using subtraction. So here we're given that log of t equals 9 and log of n equals 5. How can I find the log of t divided by 5? Well, we just talked about that being the same as separating them by log of t minus log of n. So that would be just 9 minus 5, which is 4. This is correct and super useful, but a lot of times people try and apply it when you're dividing two separate logarithms by each other. So you can only apply this property when it's one log and you're dividing two different values inside of the log. If you've got two separate logarithms, this is not the same as that where we can just subtract. Instead, all I can do is evaluate log of t, which I know is 9, and evaluate log of n, which we were told is 5. So it's two very different situations, and it's important to keep those separated. So this, super useful. We can subtract into two logs with subtraction. This we cannot. We just need to evaluate each one separately and then simplify if possible. Okay, so example 7, we've got a couple different things happening. This is saying expand, meaning separate this into as many separate logs as possible. And then part B is saying to simplify, which would mean condense it into something as simple as possible with maybe one log. So on part A, if we expand this, the first thing we can do is take this 2 and bring it down in front. So that's the same as 2 times the log of 5/3. Well, if we're taking the log of something with division, we've got the opportunity to split that up. So this would be the same as 2. And the tricky part here is 2 is being multiplied by this whole logarithm, which means when I split up the log, I need parentheses because the 2 applies to both of the logarithms. So that would be log 5 minus log 3. And then you could split that up a little bit more just by writing it finally as 2 log 5 divided by, or minus 2 log 3. So that's as expanded as that logarithm can get. So in part B, we're going to go in the opposite direction and we're going to condense it or simplify it. So we've got log 5 plus log of 20. Well, we should hopefully remember we've got the same base on both of these logs and they're separated with a plus. That means we can kind of go in the opposite direction and write that as one logarithm. And if they were being added together here, we can actually write that as the log of 5 times 20. And we can continue simplifying because we know that 5 times 20 is 100. So we've got the log of 100, which we can also simplify because log, remember, is base 10. Log base 10 of 100. So think about this in terms of an exponent. The base of 10 raised to what power equals 100? That would mean x equals 2. So this whole thing just equals 2. Okay, in this last example, we have no actual numbers in here, but we are told to expand this out. So first we can start by using the subtraction because we've got that first log with a division symbol in there. So that would be the same as log base c of b minus log base c of c. And then we've got this next piece here, which is plus, and we've got another, we've got another fraction here, so we can write that as log base c of c squared minus log base c of b. Okay, so let's look at something that we've got going on here. So we've got, first of all, we've got this log base c of c. Remember, if you've got a log with a base of the same thing as the exponent, remember there's just a 1 up there. So log base c of c, log base x of x, that just cancels out to equal 1. So really that just equals minus 1. Then we've got log base c of b minus log base c of b. Those are going to cancel out. So all we're left with is this right here. So not that minus sign. So what I can do is take this 2 and bring it down front. So I've got plus 2 log base c of c. But remember, log base c of c is just 1. So really we've got negative 1 plus 2, which is 1. So all of that mess just equals 1. All right, this next example is on how to graph something that's not common log, because the log button that's programmed into your calculator is common log. So if you've got log with a base other than 10, like 5, you need to use change of base, the change of base formula. However, nowadays most calculators, if it's a TI-84 plus or above, you can actually manually change the base of the log, but on the calculators that I used throughout high school and college, that didn't exist yet. So we had to rely heavily on the change of base formula, and it's actually really easy to remember. So we'll go through an example first, and then we'll write the actual formula for you. So say I wanted to graph y equals log base 5 of x. Well, let's rewrite this as an exponent, because I can do that with any logarithmic thing, a function. I can rewrite it as an exponent. The base of my exponent would be 5. The power of my exponent would be y, and it equals x. So this must be true. Well, if I want to solve for y, even though I know that I have the solution for y right here, but let's apply the log base 5 to both sides. Actually, we can just use common log because we want common log involved here. So if I just apply the log function to both sides, so log of 5 raised to the y equals log of x. So you can apply the same function to both sides of an equation. Then this y right here, from properties of logs, we know it comes down in front. And we've got log x here. Then I can solve for y. So remember, we're working with common log now. So we did, let me explain this again. We started with this, we rewrote it as an exponent. Now we're not stuck with log base 5. Now I'm taking the common log of both sides. So this is common log. And then I can just solve for y by dividing both sides by log 5. So I have log x, common log, divided by common log of 5. So I can't, well, typically you won't be able to type this in on a calculator, but you can type in common log of x divided by common log of 5. So the formula is, I think it's easy to remember. You can have whatever base you want. Typically we're just going to convert to base 10 because that's what's programmed into our calculator. But if you look at these numbers, so here's x appears right here on top there. So whatever you were originally taking the log of, you're still taking that log with the common log in the numerator, and then in the denominator, you're taking the log of your old base. So to change base b to base a, log base b of x. So if I want to change it to base a, then that's going to be log base a of whatever you were taking the log of originally, divided by log base a of your old base, b. And that's it. So I just find that easier to do than manually changing the base, because I just think of, okay, log of this divided by log of that, and then I'm good to go. Okay, this last section of notes is on just solving exponential and logarithmic equations. So you're going to see some of these, well, really the first one is just an exponential equation, and all the rest are logs. But just let's skim through these first. Look where x is. Sometimes it's the base of the log. Sometimes it's the answer. Sometimes it might be whatever you're taking the log of. So it's always going to be in a different spot. You want to pay attention to where is x. If x is in an exponent, then you're going to need a log to solve for it. Like in example A. We want to solve for something that's in an exponent. The only way we can get that out of there is by applying logs to both sides. the easiest way to get that x out of there would be to solve or to apply log base 2. So you can kind of just be clever about or think about what's helpful to us when using logs. We know that when you take the base log of a base of that same base, it cancels out. Log base 2 of 52. So that's one way to do it. We know that this x will come down in front, and log base 2 of 2 cancels out. So we are left with x equals log base 2 of 52. Well, how can I evaluate that with my calculator? And that goes right back to the change of base formula. So you can go and manually change the base if you know how to do that in your calculator. But I want you guys to get in the habit of using the change of base formula, so where we can just type in common logs. So this would be the same as typing in common log, or just regular log of 52, whatever you were taking the log of first, divided by the log of your old base, which is 2. And that's it. So now you can just type in log 52 in parentheses divided by log of 2. So you should get 5.700, so 5.7. All right, and now I'm gonna do this one and this one, since they're slightly different from each other, and then leave the last 3 to you so you can try doing these on your own. So this first one, log base x of 41 equals 3. The best way to do this would just be to rewrite it as an exponent. So the base of my exponent is going to be the base of the log, x raised to the 3rd power equals 41. So I'm just rewriting that as the exponent. How do I get x by itself here? Well, right now what's happening to x is it's being raised to the 3rd power. I can undo that by raising it to the 1/3 power. So times that, or raise that to the 1/3 power. Or you can think of it as cube root. We're cube rooting both sides. So all you need to do is type in the cubed root of 41 or 41 raised to the 1/3, and you'll get your solution. X equals about 3.448. So C is similar to that one. So I'm going to skip that and let you try it. And then part D, X is in a different place. So right now X is right there. Well, let's just continue what we had tried before. 3, the base of 3, raised to the x equals 15. So I rewrote it as an exponential equation, just like I did here. With this one, where was x? It was down here. So all we had to do was take a root. In this one, pay attention to where x is. That's super important. So I'm going to I usually write that down. Pay attention to where is x. If x is in an exponent like this, you need logs. You just have to use a log to help. Or, I mean, there's a quicker, way faster way to do this, but I'll get to that in a minute. But if you do this first by writing it as an exponent and see that x is there, you need logs. So we could do log base 3 of 3 to the x equals log base 3 of 15. Look where that gets us. Right back to where we started. So the way easier way that I was explaining or mentioning, right now all we need to do is change that base to base 10 and we're done. So don't overthink these sometimes and go into autopilot where you always try and make it an exponent first. Because if we know that x is right here, it's not an exponent, I've got a log, all we need to do is change that to log of 15 divided by log of 3. And that's all we need to do, which is about 2.465. So that will follow directly with E and F as well. So try C, E, and F, and then you can check your work with mine, and then we'll move on. All right, so there's those solutions for you to check your work. And then on the next page, if you look at the next one, it's just titled, this is a page that I usually assign as an in-class assignment or for extra credit. So I'm not going to walk through these one at a time. Some of it's a review. You'll see right here, we're just simplifying an exponential expression. Again here and again here. Then you're going to simplify some logarithmic expressions. And then down towards the bottom, doing some more simplifying and expanding, and then solving exponential and logarithmic equations. So it's kind of an overview. If you want some extra practice, I really suggest that you do this page. What I'm going to do is just pause my video, do all of the work so that you can see it, and compare some answers. Even if you just pick a few of these that you're maybe feeling unsure about, it would be some good practice just to help yourself feel a little more confident with some of this work. So this is not necessarily a mandatory page of notes, but a great way to practice with some of these. Okay, so I've just filled in all of my work, which is a lot, so I'll just scroll up here. So now you can see the top half of the page. You can pause at this point and check your work if you did any of these, and then once you're ready, you can pause again and check the rest of your work.